The second special case is that the circuit contains the dependent sources. Similar with the node voltage analysis, we deal with a circuit containing the dependent sources with two steps. In the first step, we consider the dependent sources as the independent sources. For instance, in this circuit, we still choose its meshes as a set of the independent loops and write loop current equations. For loop A, its self-resistance should be 1 plus 3, that is 1 plus 3 times IA, and the mutual resistance with loop B should be minus 3 because the two loop currents flow through the resistor 3 ohms in the opposite directions. It should be minus 3 times IB. There is no common branch between loop A and loop C, so their mutual resistance is 0. The right side is the voltage rise along the loop direction. It should be 2. Next, look at loop 2. The mutual resistance with loop 1 is also minus 3, so it is minus 3 times IA. Ending its self-resistance, which is 3 plus 2 plus 1, so it should be 6 times IB. The mutual resistance with loop C is minus 1 ohm, so that is minus IC. The right side is a voltage rise across all the voltage sources along the loop direction. Now we consider the dependent voltage source as an independent voltage source temporarily and pay attention to its reference direction. So it should be minus 3 times U2. Look at loop C. Its mutual resistance with loop B is minus 1, so that's minus IB. Its self-resistance should be 1 plus 2, that is 1 plus 2 times IC. The right side is the voltage rise across the voltage sources along the loop direction. So here should be 3 times U2. Okay, now there are 3 equations with 4 unknowns. In addition to the 3 loop currents, there is a controlling variable U2. Then we need a new equation. Because now we write equations in terms of the loop currents, what we should find is the relationship between the controlling variable and the loop currents. Let's have a look where U2 is. It is the voltage drop across the resistor 3 ohms. Its characteristic with the loop currents should be that U2 equals 3 times, pay attention to the reference direction, so IB minus IA. We mark this as equation 2 and substitute it into equation 1. We can get this equation. Please note that the coefficient matrix of the loop equations we get finally is no longer symmetrical due to the existence of the dependent source. As we mentioned earlier, in the case of the no dependent sources in the circuit, the coefficient matrix of the loop equations is symmetrical. In general, this matrix is no longer symmetrical if there is a dependent sources in the circuit. By solving these equations, we can soon determine the 3 loop circuits. Our ultimate goal is to find the current of each branch. As we said before, the loop current doesn't exist in real circuits. It's only a hypothetical variable for solving the circuit. By the end, the branch currents can be expressed with a linear combination of these loop currents. For instance, in this circuit, I1 should be equal to IA, while I2 should be IA minus IB. Notice that only IB flows through I3, so I3 equals IB, I4 equals IB minus IC, and I5 equals IC. Now the whole circuit is solved. Finally, we make a comparison among the 3 methods, that is the branch current analysis, the loop current analysis, and the node voltage analysis. Firstly, let's have a look at the number of the equations they required respectively. We talk about the circuit consisting of N nodes and B branches. For the branch current analysis, it needs N-1 KCL equations and B-N plus 1 KVL equations. The total number of the equations is B, which is equal to its number of the branches. For the node voltage analysis, as we mentioned before, the KVL equations are satisfied automatically, so we don't need the KVL equations, but the n-1 KCL equations are necessary. So the total number of the equation is n-1. The KCL equations are satisfied automatically in the loop current analysis, therefore we don't need to write the KCL equations, but the b minus n plus 1 KVL equations are necessary. The total number of the equation is b minus n plus 1. After knowing the number of the equations required by each kind of the analysis, we should make a reasonable choice when analyzing the complicated circuits. Reduce the number of the equations as many as possible so as to simplify the solution. Secondly, for a non-planar circuit, it is easy to choose the independent nodes because except the selected reference node, the remaining n-1 nodes are a set of the independent nodes. However, it is more difficult to choose a set of the independent loops. So for the non-planar circuit, we usually apply the node voltage analysis. Both of the node voltage analysis and the loop current analysis have been widely applied in the computer simulation software.